Today's experimental mathematics seminar of Radix University speaker is Greta Panova from University of Southern California, who will talk about sorting probabilities for Young diagrams. As usual, if you have questions, you are welcome to unmute yourself and ask the question. Then please mute yourself otherwise. Thank you.
Thank you very much for inviting me. Thank you everyone for coming to my talk. And as said, please unmute yourself and ask directly the questions. And feel free to interrupt at any point. And actually, it's better if we engage in a conversation. Make sure that everybody understands. So today I'm going to talk about. The title is about sorting probabilities for Young diagrams. So a little bit of a background. I come from the field of algebraic and enumerative combinatorics. So I like counting standard Young tableaux, for example, and calculating Schur functions. But recently we encountered this field of linear extensions of partially ordered sets, which is somewhere between an enumerative combinatorics and graph theory, and problems there are much harder because there are not so many tools and nice formulas like the ones we have in algebraic combinatorics. And it was interesting to combine the two areas and see what comes out. So the talk is half going to be about partially ordered sets and half about standard Young tableau, and so feel free to ask any questions if you don't know either of these fields. So I'll try to cover everything, of course, all the background. So let's start with the partially ordered sets, or poset, as we call it shorter. This is a collection of elements, in this case A, B, C, D, E, and some relations between them, which have to satisfy the transitivity conditions. So if A is bigger than B and B is greater than D, then A is greater than D. And if A is bigger than B and B is greater than A, then A and B have to be the same. So it's like a directed acyclic graph.
And you're assuming X is finite?
Yes. So that's a good point. So for everything I'm going to say, X is going to be finite, but of course you can define this on an infinite set. If X is finite, you can always take a partial order and totally order it in some way. So we can sort the elements so that we don't violate the partial order. So we can say, for example, here that D is bigger than E also, and add another relation, and then if we follow the arrows like this, we get what is called a linear extension. So in our notation, it's a little bit non-standard from what I was studying earlier, but A is going to be the smaller element, and the largest element is here at the bottom. So the arrows goes to the bigger element, and this is now a linear extension. So we can list our elements in order so that if X is smaller than Y, then X appears before Y in the order, or in other words, we are assigning the integers from 1 up to 6 in this case to these elements so that these integers respect the same partial order. Okay. So one thing that we as a combinatorialist like to do is count the number of configurations. So in this case, we like to count number of linear extensions. Of course, if all these elements were incomparable, we don't have any relations, we'll have n factorial, the number of permutations, so all possible ways we can label them. And if they were all ordered, so the partially ordered set was a chain, then we will have just one. And in general, the set of linear extensions will be denoted by the script E, and E of P is the number of linear extensions. And so here is an example again, so if we take this partially ordered set, so A is smaller than B, C is smaller than B, C is smaller than D, so there are three relations here. Then all possible linear extensions are listed here. There are 5 of them. And so, of course, we may ask what's the formula for this. So there is no general formula. And in fact, calculating the number of linear extensions is a sharply hard problem. So we cannot really hope for a nice formula. So what else could we try to figure out about these linear extensions? Another thing we can figure out is we can choose two elements in X and Y and in the poset. So X and Y are some fixed elements. And we will call the sorting probability of these two elements. So actually, well, let me just state. Yeah, so the sorting probability of the elements is just going to be the probability that if we take a uniformly random linear extension, then X has a smaller value than Y. So let's look at this example here. So we take this poset, which is on A, B, and C, very simple, just 3 elements, 1 relation. And we can choose A and C to be our X and Y. So these are the special elements. And what is the probability that A is less than C? Well, we look at all possible linear extensions and we choose the ones where the value at A is smaller than the value at C. So here 1 is less than 3, here 1 is less than 2. And there are only 3 linear extensions, so the probability is just 2/3. Okay. So what can we say? So first of all, why is this any good? Why do we care about this? So this was back in the days. There was a motivation that this if we had some X and Y which are sufficiently, let's say, independent, so their sorting probability is somewhere close to 1/2, then we can find using at every point such elements, we can have an algorithm for sorting the entire partially ordered set in log of E of P, the number of linear extensions time. So this is some motivation. This not, we are not what. So then the question is it possible really to find such elements always so that the sorting probability for these two elements is somewhere close to 1/2? Here is a conjecture, which has a famous name, the 1/3, 2/3 conjecture, and it even has a Wikipedia page about it. So the conjecture says that for every finite partially ordered set, and it's important that now the partially ordered set is finite. If it's not, then this conjecture does not hold. There are some degenerate cases. And if it's so then there are always, and if this is not a total order, so not all of the elements are comparable. So if there exists at least 2 incomparable elements, then there will be 2, so for which this probability, this sorting probability, is between 1/3 and 2/3. And in the example that I showed before, it was exactly 1/3 and 2/3. So the probability that A was smaller than C was 2/3. And this is really what people believe is the borderline case.
Could I ask you a question? What do you think of when you think of X and Y? Are they, for instance, representative typical elements, or especially unusual? I'm thinking of the king chicken kind of theorem. What are X and Y going to be? when you find them?
We don't really know, and actually that's part of the problem. It's not clear what you need to choose. I mean, so I will show you some examples in which we choose, we can find the X and Y, but it's not something like there won't be necessarily two minimal elements or two or part of the maximal antichain or something like that. So it's not really clear which ones they should be, and this is part of why this problem is hard, I think. So I will.
So I assume it is still an open question. It's still open.
Yes, yes.
Okay. So
Yeah.
in your talk, you'll do special cases.
Conjecture. We did not solve it. It's not. Yeah.
Will you solve special cases, maybe?
Yeah. So I will tell you.
Okay.
What things? Well, so we did things related to this conjecture, but we did not solve it. Yeah. So it's. I'm not sure actually we are closer to figuring it out than we were 30 years ago. So
But you got some interesting mathematics in the way. That's also.
So of course, so these conjectures actually motivate a lot of interesting mathematics. So I'm gonna tell you. I'm really using this conjecture, I admit, as a motivation for everything else I'm gonna tell you today. So even though we are not gonna solve the 1/3, 2/3 conjecture, when you try to solve this conjecture, you will understand that there are all sorts of other questions related to partially ordered sets and linear extensions that are very interesting and worth understanding.
So let's hope that it's never been solved because it's so fruitful. Okay.
Yeah. Right. So yeah, so this is probably one of the most important problems in order theory, in the combinatorial theory of posets. And here are some partial results. So Kahn and Sachs, who are at Rutgers actually, proved slightly worse bounds. So it's 3/11 and 8/11 is not quite 1/3 and 2/3. And the proof is it uses somewhere in the machinery, and it uses mixed volume inequalities, Alexandru-Fenchel inequalities, which is a very intransparent machinery from convex geometry, and it's not, and it does not, these bounds cannot be improved using this method, and so it's quite mysterious. Then later, again using convex geometry, but with different in a different way, the bound was improved. So you may or may not see whether this bound is better than 8/11, for example, but it is. And when we talk about special cases of the various types of posets, yes, this has been proven. So we know it for width 2 posets. Width 2 means that the largest antichain has 2 elements, and various other special cases. And in particular, when our partially ordered set is a Young diagram, we know that the conjecture holds by Olsen and Sagan, and also skew Young diagram as well. Okay, so let me show you, just to give you some flavor of what kind of things come into play when we talk about this conjecture, and how we can choose these elements X and Y. Let me show you how, I will first show you a proof how to do this for a straight Young diagram. And then, yeah, for rooted trees, it's known, yes. And yeah, so I will now focus on special types of posets which come from Young diagrams. So let me tell you, first of all, if you're not in algebraic combinatorics, you may not know all this terminology. So let me introduce you briefly to what I do on a daily basis. So Young diagrams are visual representations of integer partitions. Integer partitions are sequences of weakly decreasing non-negative integers which sum up to n. So that's a partition of n. And we represent them graphically as Young diagrams. So the Young diagram is going to be just a stack of boxes. Each row has as many boxes as the corresponding part. So 5 boxes, 3 boxes, 2 boxes. And as you can see, the border of this Young diagram is some kind of monotone lattice path. And then in algebraic combinatorics, the very standard objects are the Standard Young Tableaux, which are actually linear extensions. But we define them by assigning the numbers from 1 up to n, in this case 10, in the boxes of this diagram, so that the numbers are going to be strictly increasing along rows and down columns, and each number appears exactly once. So here is an example of a Standard Young Tableau of shape. So the shape is just the partition lambda. And we denote the number of this Standard Young Tableau by f lambda. This is standard notation. And if lambda is a straight shape, we actually have a very nice hook length formula for this. So we know something here. So this is a special type of, these are linear extensions of partially ordered sets. What is the poset? The poset that corresponds to the Young diagram. It just, the elements of the poset are these boxes, and the relations just follow the adjacency conditions for the boxes. So this is the smallest element, smaller than the box adjacent to it, and so on. And then if we have a Standard Young Tableau, it's exactly a linear extension for this partially ordered set, which corresponds to our Young diagram. So we are assigning the numbers to respect the partial order. And in this case, so for this particular Young diagram, 3, 3, it's not a coincidence that the number of linear extensions is our favorite Catalan number. Well, not like the one in the password, not all the way up to 20, but just C3. So, and we can, of course, do the same thing for skew Standard Young Tableau. So skew means that this is just the set of boxes between 2 Young diagrams. So the outer shape is this lambda, so this big shape, and the inner shape, which we bite off, is this mu, the 3, 2, 1 in this case, and everything in between we fill in with the numbers from 1 up to n, the number of boxes, so that each number appears exactly once, and the numbers are increasing along rows and down columns. So these are Standard Young Tableaux, which are linear extensions of this partially ordered sets corresponding to Young diagrams. Okay. So, so just to warm up, let's do this 1/3, 2/3 conjecture for Young diagrams. This is slightly different from the proof that was in Sagan, and also in Sagan paper, where they actually use some corner boxes. So as we said, one of the problems with the 1/3, 2/3 conjecture is that we don't a priori know which elements to choose to compare, which are going to be our best guess. But here, it's not that hard to choose some good pairs. So let's say, so I'm going to say that X is going to be this element here, the second element on the first row. So the second box in my first row diagram. And I will prove you that we can find a Y here somewhere on in the first column. Okay, so so let's look at various probabilities. So if we take a linear extension or a partially ordered set, we always, so this is this corner box will always have the value 1. And then we can choose where to put the 2. It's gotta be in either to the right or below. So if we put it here, then we know that this element is not gonna be 2, so it's gotta be bigger. So bigger than 2. Gonna be bigger than 2. And x is going to be between y0 and y1 in this case. And what is the probability that we have this situation? It's exactly the probability that x has value 2 in our standard Young tableau. And if x has value 2, it means that these elements 1 and 2, that these values are already assigned. And now all we need to do is assign find the standard Young tableau for the remaining shape over here, which is a skew shape lambda without the first two, without the partition occupied by y0 and x over f lambda, of course, because it's probability. So then we can consider the next situation. So if this is not the case, then x should be bigger than y1, and it might be smaller than y2, in which case we know that y0 is 1, y1 is going to be 2, and then x has to be equal to 3, and y2 is something bigger than 3. So then we fix the values here in this 2-1 partition, and we are calculating the number of standard Young tableau skew shape in the remaining part, and so on. In general, if x takes a value somewhere between some two adjacent elements in here, then this is going to be, the probability is expressed in terms of the number of standard Young tableau of these skew shapes. Okay, so now a few observations. First, these numbers are weakly decreasing. So why? Well, we can see it over here. This is the number of standard Young tableau of shape lambda without 2, standard Young tableau of shape lambda without 2 and 1 extra box. So we have actually a smaller diagram. So obviously the number of standard Young tableau that are in this smaller inside diagram is going to be smaller than the number of standard Young tableau of the bigger diagram which contains it. So we have this weak decreasing sequence of probabilities, and they all sum up to 1 because in the end, the worst case, we're going to end up here. X is going to be the biggest among all this, but then it's going to be just L, and the value will be L plus 2. And those are all possibilities. So this probability sum up to 1. And now let's think about what this all means. So first, Q1, we can assume that it's less than or equal to 1/2. Otherwise, we can transpose this picture along the diagonal, and then our x is going to be occupied by, the role of x is going to be played by the other elements, so y1 in this case. And then if Q1 is actually greater than or equal to 1/3, well, we already said it's going to be less than 1/2, but then we found our culprit. So x and y1 are going to be our elements of choice, so for which this probability is within 1/3, 2/3. And otherwise this is smaller than 1/3, and these are actually even smaller than that. So when we start adding them up, Q1 plus Q2, at some point this sum will go over 1/3, but because at every step we are adding at most 1/3, it's not going to go over 2/3. So the first time we go over 1/3, we know that it's actually going to be less than 2/3, and our y is going to be one among this y case. And as you can see, even in that case, we don't actually know which exactly y we're going to choose. We just know that it's going to exist. So this is a warm-up, and the reason that I wanted to show you is that there are a few things that are important here. So first of all, we need to be able, one way or another, to count how many linear extensions there are with an element having a particular value. So this comes into play. And then the other part of the argument is that we break down into various probabilities, and we can if each of these probabilities is pretty small, then we can somewhere in the middle find the thing we're looking for. Okay, so this is 1/3, 2/3. So now let's go to something more substantial. So not only do we believe 1/3, 2/3 holds, but there is actually a limit situation. So the sorting probability of a poset is going to be the minimal. The pair xy is going to be the closest distance to 1/2 that we can achieve among all the sorting probabilities between two elements. So we are looking at all pairs of elements x and y, and we are looking at these differences. The probability x is smaller than y or y smaller than x. So one is on below 1/2, the other is above 1/2, and we are looking at the minimal such distance. And we believe that this further conjecture, much stronger than 1/3, 2/3, is that this sorting probability actually goes to 0 as the width, which is the number of the size of the maximal antichain of the poset, goes to infinity. And there is a proof for when the number of minimal elements in the poset is that many. Actually, it might need to be n over log n. Okay, so but in general, if let's say the antichain is about square root of n, which is what one would expect sort of on average, then we don't really know what to do. And so we go back to our favorite Young diagrams because we know that combinatorics, and also because it's still educational, and we can prove this conjecture for Young diagrams a fixed height. Actually, in this case, the width of the poset is just d. It's a fixed number, and this conjecture still holds. So it's stronger than the conjecture, and we can show, in fact, that the sorting probability is less than some constant over square root of n. And if we want to be even more precise, if we take our favorite Catalan posets, which I'll explain in a moment, when the partition is n, then we can calculate much more precisely what this sorting probability is, and then it's actually less than or equal to c over n to the 5/4, which I don't see a way to prove in general. So C is just some constant which comes out of the computation, which I didn't want to. I don't want to write down. So C are some constants. Again, this has more. These are in some sense probabilistic. Yeah. I'll need to look into the paper what exactly came out. Okay, so how do we do this? So the main idea, other than the fact that we know things about Young diagrams, is that we can think of linear extensions as monotone walks in the grids in D dimension, where D is the width of the poset. So in this case, so here we have a poset with two chains. So the chains are alpha and beta. And here is a linear extension. So these are the numbers associated to alpha and beta. And these are also the extra relations between alpha and beta, as well as this is these are decreasing down. So now in these linear extensions, we have we do the following. So we associate to the horizontal steps are going to correspond to here alpha 1, alpha 2, and so on. And this is beta 1, beta 2, and so on up to beta 7. And we're going to do the following. So we start reading the numbers here. 1 comes to an element on the second chain. So we are going to, our first step in this path is going to be vertical. Then we go to element 2, which corresponds to an element of the other chain, so alpha 1. Then we take a step, a horizontal step. Then the element 3. Element 3 is also on this chain, so another horizontal step. Then element 4 is on the other, and so on and so forth. So you can see that the corresponding, when we number the steps in our in this lattice paths from 1, 2, 3, and so on. So the numbers in the linear extension that appear are exactly correspond to the row or column in which this step appears. So if it's a horizontal step, we are looking at its x coordinate. And if it is a vertical step, we're looking at the y coordinate. And then these extra relations between alpha and beta are telling us that our path is going to be within this region. So there is a one-to-one correspondence between lattice paths from 0, 0 to, in this case, 7, 7, that are inside the white region, and linear extensions of this partially ordered set. And in general, we can increase the dimensions if we have more chains. So if we are cutting our poset into 3 chains, then we are going to have monotone lattice paths in some kind of monotonous region in 3 dimensions, and so on. So let's go to our Catalan posets and study that a little bit better. So here is what we call the Catalan posets. So we'll see in a moment why we call them, but so these are going to be diagrams, Young diagrams n. So n boxes on the first row, n boxes on the second row. Then the partially ordered set is going to look like this. It's like a ladder. And here is a linear extension. Of course, here is a tableau, Standard Young Tableau, which corresponds to this linear extension. And just as I was showing earlier, we can associate, in this case, a dig path. So for this particular partially ordered set, the region that we are going to move in is going to be this triangle. And we can see it as a dike path, so up down path above the horizontal axis from 0, 0 to 2n 0 as follows. So we read the numbers 1, 2, 3, and so on. And if the number appears on the first row, then we take a up step. So we have 1 up, 2 up, but then 3 is on the second row, we take a down step. Then 4 and 5 are up. And then 6, 7, 8 are all on the second row, and we go down. And it's a one-to-one correspondence again in this case. So hence that's why we call it Catalan poset, because the number of these walks, this paths is exactly the Catalan number. And now say let's remember what we wanted to do. We want to see what's the probability that in a linear extension, the element x is smaller than the element y. Say x is on the first row at position A. So this is going to be our element x. So let's say it's going to be here. This is our box. And then the element y is going to be somewhere on the second row, somewhere before x. So that they should really be incomparable. And then the probability that the value at x is less than the value at y is the same as the probability that this path passes above the point with these coordinates here. And you can see this, that if it passes above, then the 8th up step that we take is going to show up before the bit down step that we'll take, and so the value at x is going to be smaller than the value at y. And so if we want to prove the sorting probability limit, then we need to look at this and this function here. So h and z we're renaming some variables. So h is going to be the position here, and z is going to be the distance of how far we are going to look for the number y, for the element y. And then if h is around n over 2 and z is on the order of square root of n, we see that this is actually very close to 1/2, which is what we really need to find in the end. And here is a graph of this function, so in 2 dimensions, and this is here 1/2 plane. And we want to find these pairs h and z, which make this closest to 1/2 and show that it's within 1 over n to the 5 over 4 of there. And so here is how it works. So there is a little bit. Yeah.
Do you have an explicit expression for this function R sub n?
Yes, we do, but it's a lot of binomial coefficients.
Okay.
Yeah. So this function can, in this case, it can be calculated. Actually, the total function doesn't have a nice closed form, but what we can calculate is the differences between pairwise elements. So for example, these differences here, so when we change h to h plus 1, this actually, using this lattice path interpretation, corresponds to the number of paths that pass from here to here. So these are the red paths minus the paths which pass from here to here. And of course, using the reflection principle, we can calculate these paths as some products of binomial coefficients. We can find the difference and analyze it precisely, and then we'll get some kind of inequality. And I'm hiding all these constants, which we know exactly what they are, just going to be even heavier. And so
beautiful graph you get by doing the limits for very big n. Yeah, it's very nice.
Yeah, so in here and here, of course, this is the semicircle law that we see in this. If this red cut we'll see the semicircle law. And what so the point of all this is that now we can sandwich the steps in this, the way that the function changes. The steps are pretty small, especially when h is n over 2 and z is on the order of square root of n. We can see that the changes are pretty small. So then, similar to the reasoning in the beginning that I showed with the 1/3, 2/3 conjecture, we can, when we start changing the steps, we can actually find that we are going to cross 1/2 at some point, and the interval on one side of 1/2 and on the other side of 1/2, so the total size of the interval is going to be at most some constant over 1 n to the 5/4 in this case, and this is basically how the proof goes. So yeah, and so here there is some explicit binomial coefficients which enables us to do this so precisely. So let me tell you how these things work in general. There isn't much time. So here is our more general theorem. So we have an arbitrary Young diagram with d rows. And for some technical reasons, we are assuming that these rows are somehow linearly proportional with n, and including the last one. And now, again, so the hard part is to find the good elements x and y, and we are going to look for them x on the first row and y somewhere on the second row, just like with the Catalan posets. And so here are some. So if this is our poset here, which is pretty small. So the partition is 4, 3, 1. Then we are going to look at the linear extensions where x is smaller than y. So these are going to be Standard Young Tableaux where the value here is less than the value here. So 4, 7, and so on. And the other linear extensions where the opposite holds. So here are some examples. So these are going to be for Standard Young Tableaux. And now we make a few observations. So first of all, the intuition again comes from this correspondence between linear extensions and lattice paths in a simplex, very generalizing the Catalan case in ZD. So d dimension is this number, is the height of the Young diagram. And then, as I said, we choose x in the first row, y in the second row. And again, when we think of terms of these lattice paths, the probability that x is smaller than y is equal to the probability that the lattice path passes on one side the codimension 2 hyperplane. So this is like the generalization of the points in 2 dimensions. And so now we use some intuition from probability, and in particular Hoeffding's inequality, which limits the tail distributions of how likely is it that the random wall goes far from certain points. So this tells us that most lattice paths that we care about are going to be concentrated somewhere in the middle, informally speaking, and then we have to estimate this. So we estimate this sorting probability as follows. So this Hoeffding's inequality is going to tell us that we need to look at just what's happening in the middle of our Young diagram, and this mu and lambda over mu is somewhere around half of the partition lambda, and this is basically where on the border of mu the elements x and y are going to be. And then finally we need to somehow calculate this sum, and then we use tools from algebraic combinatorics to do this. So So let me just show you in one more minute what this is about. So this is again the last sum from our inequality. So after some simplifications, reductions, and so on, we are left with estimating this sum. The number of Standard Young Tableaux of this shape here times the number of Standard Young Tableaux of this shape here, where mu is about halfway between half the size of lambda over f lambda. And how do we do these estimates? Well, we use one of our earlier formulas. This is what we call the Naruse hook length formula, which gives us the number of skew Standard Young Tableaux as n factorial times a positive, so it's a positive sum over what's called the excited diagrams, and then for each excited diagram we have a product of hook lengths. So excited diagram, it can be described algorithmically as obtained from starting mu inside lambda and moving boxes along from mu along the diagonals, if it's possible to do that. So for example, here in this is mu, this is lambda, and we can move all these boxes here. So we are going to get this excited diagram, and then we are going to calculate hook lengths within lambda for these boxes, and this is going to be the term in the product. So these are the hook lengths here. 6, 5, 3 is the distance to the here. 5 is the distance along rows and down columns, down the column to the border lambda. And so here is another example. So this is the zigzag skew Young diagram, which is actually corresponding to alternating permutation and is enumerated by Euler numbers. And in this case, the number of such Standard Young Tableau would be 61, can be given by this formula. And the punchline here is that for this we can do a pretty tight control on how many excited diagrams we have and how large each of these terms is, and this enables us to do what we did. And so I'm going to stop here since we have 2 minutes for questions.
Thanks. Thanks for a great overview of a beautiful approach to this very important special case of a famous conjecture. We have 1 minute for formal questions, and after this, people are welcome to stay for informal questions. Are there questions for Greta? So I have a quick question for the Catalan case. That is it best possible the 1 over n to the power 5 over 4? It's sharp.
So yeah, I think so. This is not good. It's not possible to improve it for every n, and probably there is some number theoretic issues also involved.
And in general, the 1 over square root of n is not necessarily sharp, right? You don't know if it's
no, it's just as good as we can estimate it, but it's probably better than 1 over square root of n.
And one other quick question regarding the Catalan case. Can you do something analogous to Motzkin paths?
I'm not sure this would correspond to some linear extension, but of course, we can do something similar there also. Yeah.
Okay, thank you.
Yeah.
Greta, I have a question. Is there a kind of relative it seems to me you can make a kind of relative version of this sort of sorting probability where you say fix a linear extension of a poset and you look at its Schützenberger promotion orbit, and then just measure the probability of x being smaller than y within that orbit. Is there a 1/2, 2/3 conjecture which is valid in that case, or?
I don't think anyone has looked into that, but thank you very much for the question, because we are just writing a paper about promotion. So So this we'll take a look if it makes any sense in that case, if we can make a conjecture. Of course, I mean, since we are in the experimental math seminar, one of the questions is, can we actually generate sufficient data to see how things behave, right? So this computationally difficult problem, as I said in the beginning.
Well, thanks so much. This ends the official part of this talk. Robert, please stop recording, but people are more than welcome to stay and ask